All right, so let's kind of look at what these kinds of questions might end up looking like. So here's one that is a pretty good intro. So wheel has a radius of 0.25 meters and spins at 18 rads per second. So the omega is 18 rads per second for 12 seconds. Now it's asking, assuming that it is slipping, how far does it go? Okay, well, whenever it's asking how far the wheel rolls, it's really talking about, you know, if you're going to measure how far the wheel rolls, it starts here and it goes here. So you're really measuring it based on its, center of mass, right? Sort of. Okay, so it started there. It's going to end up over here. And we want to know what is that length. Okay, so this actually isn't too bad. So remember we talked that the velocity of any point, so you have this instantaneous center of zero velocity because it's not slipping, so it's not moving, it has to stick in order to roll forward, that the velocity of any point is going to be that perpendicular distance r times the omega of the object. So we're able to say, let's call this point P. We can say that the velocity of P is going to be omega times r. Okay, so in our case, omega is 18, r is 0.25. So I'm going to go stick that into my calculator. 18, come here, turn on. Oops, 18 times 0.25. I guess I could have done that in my head. Shush, science is fun. Wait, that doesn't make sense. Wait, 2 times 2. Did I type in the wrong answer after all that? Yeah, I did 8 times 2. 18. See, this is why I don't do things in my head, because ultimately something bad is going to happen. So, come here. I'm trying to move it so that you can actually see, except not quite that crazy. There we go. 18 times 0.25, so 4.5. That makes more sense. Okay, so this thing is going, because this was in meters, and remember that radians are kind of like a fake unit. So this is in meters, and this is in radians per second. So the radians kind of go away, and I end up with meters on top and seconds on bottom. So again, the units are all consistent. My velocity at that point P is 4.5 meters per second. And now it's a really straightforward question, because what the question is really asking is, if something is going 4.5 meters per second, how far does it go in 12 seconds? And we know that the distance traveled is the velocity times time plus any initial position, but there's no initial position here. So we have velocity times time, and again, meters per second times seconds, so the seconds cancel out. We have meters, so whatever that times 12 is, 54 meters. Okay, so working these out shouldn't be too bad. Now, what if instead of giving us a radians per second, what if it actually gave us revolutions? So, like sometimes whenever we talk about things, we say after it rolls 3 times, after 3 revolutions, how far would it go? After 3, or like, let's say revolutions per second. So that way we're still dealing with velocity, angular velocity. So what if instead of saying, 18 rads per second, it told us 3 revolutions per second? So the big thing here is we need to remember that revolutions is not just like radians, but we can convert it. So there are 3 revolutions per 1 second. 1 revolution, so basically we need to go, well, how long does it take to go all the way around? Well, it takes a circumference, and the circumference is, so the circumference is twice pi times r, so 2 pi r, and if you want to call it radians, because you like having that on there, the revs cancel out, and my r was, I already forgot, something 0.25. Come here, girl. So it would be 3 times 0.25 times 2 times pi. So 942, I think, if I did that right. 3 times 2 pi times r. Was it 0.5? I already forgot. Was it 2.5? See, this is why I should never be in charge of anything. 0.25. So this is 0.25. There we go. I knew I did something silly. So 3 times point... come here. Come here, you silly calculator. 3 times 0.25 times 2 pi, 4.71 rads per second. So 4.71 rads per second. So you could solve the problem kind of basically just the same, just knowing to do rads per second instead of revs per second. All right, let's see. Anything else interesting we can do with this problem? Now let's leave that one for the moment. Now let's do this one. Okay, so a car travels 30 meters per second and the tires rotate. Oh, there's our rads per second. So before I even go any further, I'm going to convert. Oh, but it doesn't tell me what the radius is. Well, you know, I'm just going to have to... Oh, wait, that is rads per second, not revolutions. I'm not paying attention. 95 rads per second. There we go. And a car travels 30 meters per second. So what is it really saying is that center travels at a velocity of 30 meters per second, right? Okay, so if the velocity is 30 meters per second, and I know how fast the tires are rotating, then again, V equals omega R. So I have 30 equals 95 R. So 30 divided by 95, 30 divided by 95 is going to give me 0.316. So I have a radius of 0.316 meters, and that would be the radius of the tire. Does that make sense? And now if it asks me, you know, how far does it go, in what amount of time, basically now that I have ways to convert this V and the omega and the R, once I have a V, then I can answer questions that have, you know, 1/2 AT squared plus, well, not A because I don't have that yet, but I can go V equals V naught T plus, or X equals V naught T plus original X naught. So I can say how far it goes because I have the velocity and stuff like that. So really there's only so much we can do with these to make them complicated. But essentially what you're doing is you're just taking this relationship and making sure that you really understand what's going on here. Here's another one that I have. If I can scoot it over. Come here, Scooty Scoots. Well, you really don't want to go over there. Okay, hold on. Okay, there we go. A wheel has a radius 0.28. It starts at angular velocity 10 rads per second and accelerates at 3 rads per second squared for 5 seconds. Okay, so remember we had these, and we need the final linear speed. Okay, so remember we had the ways that we could associate stuff. So from the last chapter, chapter 10, we had, what do you call it? Omega equals omega, omega equals alpha t plus omega naught. And that's the friend of velocity equals acceleration times time plus initial velocity. So remember these equations are friends. So we have these that go together. So if it starts, so basically what we're going to get is we're going to get the final linear or the final angular velocity and then convert that into linear speed. All right, so I have an angular velocity that starts at something and then it goes for that. Okay, so 3 rads per second, and if you want to watch your units, I'll put them below so they're not quite as confusing. 3 rads per second times, or second squared, times 5 seconds. Okay, so the seconds cancel out and I end up with rads per second. So that's good, that's a velocity. 3 times 5 plus the initial angular velocity, 15 plus 10 is 25 rads per second. So if we're going 25, rads per second, assuming no slipping. What is the car's final speed? We can say, okay, well, the car's final speed is V equals omega R. V is 25. Omega is 20. Sorry, V is not 25. V is what I don't know. Omega is the 25 because I was looking at the units. So the units are always saving me on this. So rads per second. The radius is 0.28, and that's in meters. So I'm going to end up with an answer in meters per second, so that's good. So I've got 25 times, I already lost it. Come here, girl. 25 times 0.28. So I get 7. Okay, so 7. The final is 7 meters per second. Okay? So if you're interested, we could use this and we could say how many rotations of this car was there. So how many rotations? So if we're looking to calculate the number of rotations of the thing, we can say, well, how many thetas did it go through? We say, well, theta is 1/2 alpha t squared plus omega t plus theta naught. And that, of course, is a match to the 1/2 at squared plus v naught t plus x naught, right? Okay, so we can use those same equations if it asks, how many times did the tire turn? So the theta is going to give you the total number of revolutions, the total number of turns, or the radians, not the revolutions, get the total number of radians that it goes through. So then we can work backwards. The question isn't asking this, I'm just trying to give you some extra content. So the total theta that it ends up going through is 1/2, I already forgot A is 3. Okay, so 3 times 5 squared plus 10 times 5 plus 0. It starts out at 0. So I've got, I really should figure out a way to put this somewhere that I can actually see it every time, but that's okay. So 25 times 3 divided by 2 plus 50. Again, I probably should be able to do that in my head. Oh, thank you. 175 over 2. 87.5. So this goes through 87.5. Now the question is, what are the units? Okay. So this was rads per second squared, and this is second squared. This is rads per second. This is seconds. So the answer is in radians. So it goes 87.5 radians. So if I actually cared how many revolutions it went through, I can say 87.5 radians. 1 radian is, well, 2 pi radians, I'll do it that way. 2 pi radians is, or 2 pi r radians is 360 degrees. It's 1 revolution. There we go, that's where I'm going. I'm going radians to revolutions. Radians to revolutions, there's 2 pi r radians in 1 revolution. So 87.5 divided by 2 pi, and then the r that I was given was 0.28. Okay. So I've got 87, come here, girl. This is just silly. 87.5 divided by 2 times pi. Where did it go? 2 times pi times 0.28. And that's 49.8 or 49.7 revolutions. So basically the tire turns essentially 49.7 times. It makes 49.7 full revolutions in order to get where it's going. So basically, if you have those equations down that we practiced previously where we were converting, rotational to translational, and using this stuff with the tires, that should give you a pretty good start in figuring out where to go next.